Hello there, this is Emerald Snippets.
And today we're going to show you how we built an NLP classification model for programming languages.
But before we dive into the details, let's sneak a peek at the final deployed model. Now this is our demo version for our final model. Let's just try it out on some code snippets as a proof of concept. We can use this example of Python code source. As expected, the predicted language is Python. For the second example, here's a JavaScript code source. Again, the model successfully predicted JavaScript.
So if you're interested in what you just saw, we will be explaining exactly how we got our model step by step from the dataset building phase to the final results analysis.
Before we start building our model, don't forget to hit that like button and subscribe to our channel if you like the content and would like to see more data science projects like this one. And now, let's jump right into it.
Let's start with preprocessing. So, most machine learning classifiers take a feature vector of fixed length as their input. What we've got here is code snippets. So the question is, how are we going to convert unstructured textual data into a numerical array of fixed length? The first part of our answer is tokenization, which is extracting words, or what we call tokens, from textual data. Scikit-learn's default tokenizer is built mainly for natural languages, such as English or French. This is not adapted to our use case, which is why we built our customized tokenizer using Regex to get from this to this. Our customized tokenizer is going to target three main categories. The first one are variables, module names, and keywords. The second one are operators such as the equal sign. And the last one are tabs, spaces, and your typical brackets. In the next sections, you'll get to see the code we use to switch Scikit-learn's default tokenizer with our own. But for now, let's have a visual demonstration of the regexes we used. So the first category of regex of tokens that we wanted to select are variable and module names. And as you can see, the regex selected exactly that. However, we chose to escape names or strings starting with numerical values such as 15 pixels here. The second category of tokens we targeted are the operators. So the regex we used is the following. It's mainly a list of operator characters. And the last category is your spaces, tabs, brackets, and quote literals. So the regex we use is also just a list of the corresponding characters.
So let's see how we do this in code. You can see here that I've already imported my data and split it into train and test sets with a test size equal to 20%. Now I'm going to copy paste my token pattern from my cheat sheet and run it. And now we're going to build our vectorizer, which is TF-IDF. I'm going to import the package and then just build my vectorizer just like this. So vectorizer equal to TF-IDF, and here we have two parameters to define. The first one is the token pattern, which is our customized tokenizer, and the second parameter is the max number of features, and we're going to choose 3000. Now we just run it. The next step is to fit our model over our train data. So here xtrain, and we just run it. Now this might take a while, so we're going to speed up the process. So see you in a few minutes. Okay, our model is done fitting, and now we can see our tokens. We are going to store it in a variable called tokens, and to get our tokens we just type tokenizer dot get feature names, just as easy as that, and we run it. Now to see them we just print them, this easy. So you can see here all the special characters, the operators actually. Here This seems to be like variable names. There are also a lot of keywords like alert, align. Now that we saw how we get our tokens in code, let's jump into the next section. Before we can exploit textual data, a good practice is to do some cleaning up. In fact, while looking through the different tokens, we noticed that there are a lot of single character variable names, or ones constituted with a sequence of the same character, such as XXX, which does not add much information to the classifier. For this reason, we chose to treat those as stop words and remove them. Those are just some cleaning up examples, but you can go further and try more tweaking if you feel it would help. Let us know if you do some changes that get you better results. Now let's build on the code we used earlier to get our cleaning function. So we're going to define a normal Python function called preprocess and give it our data as input. The output will be the clean data, and we're going to use the replace method to do this with our regex pattern as input. I'm going to copy paste it from my cheat sheet here and tell the replace method to replace it with an empty string, and then tell it to consider it as regex by typing regex equal to true. The same goes for the second regex pattern. Again, copy paste empty string regex equal to true, and we run it. Okay, it's good. Next, we're going to build our transformer, and before we do that, we have to import the function transformer package from Scikit-learn, and then we just define our transformer by typing function transformer and giving it our function as input. That should do. Now if we want to test it, we can just type some random code with the patterns we wanted to delete. For example, we can import pandas, and then use the patterns we wanted to delete, for example, for A's and X equal to 1. Now to test our transformer on this piece of code, we're going to print the output after the transformation. So we're going to type transformer dot transform, and we're going to put our code in a list. Before the print, I'm going to take the first output. Now you can see that here it deleted both the sequence of the same character and the single character.
Vectorization. So to perform the vectorization, we use TF-IDF vectorizer. A quick reminder of how it is computed for each token in a document. Well, it's the product of the term frequency and the inverse document frequency. In our case, documents are code snippets and tokens are the ones we extracted in the previous part. So to sum up, this is an overview of the complete preprocessing pipeline. First, what we've got is code snippet here, then we preprocess it by removing what we think are stop words, then we get to tokenization part where we separate our code snippets into tokens, and the last part is using the TF-IDF vectorizer to get an array of fixed length. So let's get to the code part. So as you can see, we've already defined our vectorizer here in the tokenization part. So what we used is the TF-IDF vectorizer, which had the tokenizer integrated. And also, we've already defined our transformer. So what we're going to do here is to put it in a nice pipeline that we can use then simply. So let's first import it, then define our preprocessing pipe. Oops, typo. The first part is the transformer, which is going to clean the stop words. And the second one is the vectorizer, which is going to do the tokenization and the vectorization. I'm gonna call it the vectorizer. I think this should be in a list. So let's do this. And there you go. Here's our pipeline ready to go.
We now get to the classification part. To choose the model that best fits our use case, we're going to make use of Scikit-learn's grid search to compare different choices of classifiers. The next step is to define our grid search. The first thing to do is obviously to import the package from Scikit-learn. Then we're going to define a second pipeline that includes the classifier. So we're going to call it, for example, CLF pipe. And for this we're going to include the pipe we already created called Preprocessing pipe. Just select it. And the same as earlier, we're going to call it Preprocessing, then the pipe, and we're going to put all of this in parentheses. And now we're going to give the pipeline the classifier, and since we have a lot of classifiers, we're going to give it at first one random classifier so we don't get an error, for example logistic regression. Now we're going to define multiple classifiers that we're going to compare, and to do this we're going to create a dictionary we're going to feed to the grid search. We're going to call it param-grid dict. The keyword is CLF and then the list of classifiers. For our example, I've chosen 3 classifiers. I'm going to copy paste from my cheat sheet. So they are logistic regression, random forest, and MLP classifier. I'm going to just put them in the list, in the dictionary. Just like that. And now the last step, which is the definition of the grid search. We're going to call it the grid search equal to grid search CV. We give the pipeline as an input and the param grid dictionary with the different classifiers. The last input is the number of folds, which is going to be 3. Now the next step is to fit our model, and for this we simply type .fit and we give it the training data. This takes a bit of time, so we're going to speed up, and spoiler alert, the chosen model will be random forest. Once our model is done fitting, to get our best model, we simply type grid search dot best estimator. Now this variable here will have the best model with the best mean score after the cross validation. And actually, if you want to see the best score, you just type grid search dot best score, just like that. Once we've chosen our best model, we want our classification to have as good a performance as possible. For this reason, we will be performing a second grid search to optimize the model's hyperparameters. Just like earlier, we're going to define a dictionary that contains the different parameters we're going to compare. So here is going to be this dictionary called param-grids random forests, and we'll have the different parameters we're going to compare. And the steps to build our second grid search are exactly the same as earlier, with a simple difference. Earlier we compared multiple classifiers, but this time we're going to compare multiple hyperparameters for a classifier. So we're going to use this keyword CLF to identify the hyperparameters we're going to compare. For example, here, for number of estimators, We put here CLF double underscore just before, and the same goes for all the hyperparameters we're inserting in the dictionary param_grid_ref. Once this is done, we just give it to the grid search as a param here, as you can see, param grid search, and we fit our model just like earlier.
Okay, now that we've chosen the best model with the best params, it's time to reveal our model's accuracy, and it's 96.8%. So let's take a look at our final model's predictions. The best example to try this on is probably the page's source code. So let's go and copy paste it. You can see it rightly predicted HTML. So to dig deeper on why it made this prediction, we can click on Predict with Explanation button, and it will get us more details about the tokens that had the biggest effect on our prediction. If you'd like to see how to deploy a demo like this for free, you can follow us on Medium, as we'll be soon publishing a story explaining exactly how to do that.
We got to the end of this tutorial. We hope you enjoyed the content and hopefully learned something along the way. Please feel free to leave feedback or any questions in the comments or response section. Thank you for watching and see you in our future tutorial.